Hello, and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 23 in the series on section 5.2a, Logarithmic Functions, Part 1. We just covered the exponential functions, and logarithms can be seen as the inverse of exponential functions. That is to say, when we compose them, we just get our input back. If, say, for example, the function 2 to the x were to take in an input of 3, raise 2 to that power, and give us 8, which is 2 times 2 times 2, then this logarithm, base 2, would have to take in an 8 and give us back a 3, reversing the roles of input and output. Any exponential equation can be rewritten as a logarithmic one, and vice versa, through the following change of form. We say that b raised to the power of a is equal to c if and only if log base b of that value c is equal to a in turn. Notice the color coding of the different roles here. We say that a base b of the exponential expression on the left becomes this base b in the subscript of the logarithm. Likewise, the argument of the exponential expression over here becomes the output of the logarithmic expression. And likewise, the output of the exponential expression has become the input or the argument of the logarithm. So the b goes down to the bottom, and the a and the c have switched sides and, in effect, switched places in the function notation. The parameter b in this expression is called the base of the logarithm, and likewise the base of the exponential. And as before, we are going to require that b not just be any old number. It must be positive, and furthermore, it cannot be equal to 1. This is to prevent having to consider complex valued, in fact, complex many-valued maps, and the kind of degenerate case where you are raising 1 to some power, which would really only give you 1, and not a true variable. If we'd like to think about the question in reverse, exponentials ask, what do I get when I raise this number to a certain power, or what do I get when I multiply this number by itself a certain number of times, if that exponent is a positive integer? Logs, on the other hand, answer the question, what number must I raise the base to in order to get a certain number, which is the logarithm's argument? There are two special bases in terms of notation. One is the omission of the base. If we do not see a base, we call this the common log, and the implied base is 10. This is very similar to the omission of the index of 2 when we use a square root symbol. On the other hand, we have this abbreviation ln, which is the natural logarithm, and it has a base of e, which is, in fact, a particular number. What exactly makes the common log common is fairly understandable. We use a base 10 system. And so raising 10 to certain powers is going to be a common setting for questions. On the other hand, what makes e, which we will address shortly, its value, what makes that so natural is not an obvious question. And in fact, we will have to procrastinate that discussion for a little bit. Suffice it to say, there are a few things you should know about this strange new constant. Well, one is that it is a constant. It's a real number, positive, and it begins as such, 2.71828, and so on. If one wanted to think about this as similar to pi, which is often abbreviated as 3.14, although we know it continues on and does not repeat, one could think about e as perhaps being approximately 2.72. But this is a rough approximation indeed. For a number that goes on forever without repeating, you should keep in mind two things about this strange new constant e. One is that it is a positive real number. It is irrational and so goes on forever in its decimal expression without developing a repeating pattern. But if we wanted to think of it as an approximate value, 2.72 is a nice place to start. The first thing we're going to want to do with the logarithm is rearrange it and figure out what that can tell us about certain powers of the base. For example, over here we have the cube root of 27 is equal to 3. This has a logarithmic expression. The base is being played by the number 27. The output of 3 is now brought inside the logarithm's argument, and the power in question here is, well, the cube root. Recall that the cube root is the 1/3 power. And so this power of 1/3 comes over to the other side of the equal sign. You want to get fully acclimated to the idea of switching back and forth between these two forms, exponential form and logarithmic form, because oftentimes a question is more easily posed one way versus the other. Recall that anything to the 0th power, provided it is not itself 0, is 1. And similarly, log of any base of the number 1 will give us 0 as an output. 0 is the number that we need to raise 7 to if we want to get 1. Here, it helps to know that 2,401 happens to be the 4th power of 7. Recall that a negative exponent basically just makes a fraction out of it and puts 1 over that 4th power of 7. Now, the base of the exponent becomes the base of the logarithm. The power of minus 4 should be brought out to the other side of the equal sign. And this, the output of the exponential expression, becomes the argument of the log. In other words, you bring it inside. Notice that sometimes I will use parentheses around my argument of a logarithm, and sometimes I won't. It depends on if I find the argument to be particularly complicated or if the mood suits me. I will put parentheses around the thing which logarithm is logarithming. Here we have another expression. Let's take care, as they have switched the side that the exponented term is on. It matters not. Equality is a symmetric relation, and this might as well have been 11 squared equals 121. Now, 11 is the base, goes here. 121 is the output, which gets brought next to the logarithm as its argument. And 2 is the exponent, which now is brought to the outside of the equal sign. 5 to the negative 1/3 power is 1 over 5 to the third, or 1 over 5 times 5 times 5, which is 125. So log base 5 of 125 is the exponent, negative 3. You can see right away that what logarithms are really doing is they are bringing exponents down out of the exponent and turning them into regular numbers. That is to say, written at the appropriate size, not tiny, and not trapped up here in the superscript. Just down on the regular old line that we write things on. All right, now let's practice going backwards from something which is in logarithmic form to something which is in exponential form. Here I have the fact that the log of in base 8 of 512 is 3. And this is precisely because 8 to the power of 3 is equal to 512. But I didn't even need to know that that was true in order to rewrite things. I needed to know that this was the base of the logarithm and so becomes the base of an exponent. What's on the other side of this equal sign from the logarithm gets brought up into the exponent, and what was the argument of the logarithm is now the output of the exponential expression, and so it gets written over here. Similarly, here we have another base of 8. That goes here. Negative 3 on the other side of the equal sign should be brought up into the exponent, and the argument of the logarithm should be brought to the other side of the equal sign. So the fact that 8 to the power of negative 3 is 1 over 512 is written either in this exponential form or in the previous logarithmic form, negative 3 being equal to the log base 8 of 1 over 512. They mean the same thing. They say the same thing. We need to get good at going back and forth between these two equivalent forms. Here we have one for ln. Recall that that's just log base e. And so e becomes our base, 11 becomes our exponent, and this x, which was the argument of the natural logarithm, will be the output written here on the other side of the equal sign. Again, we identify our base for this one, it's 4. Our output, which becomes the exponent, is 2. And our argument, which becomes the output, is 16. So we've encoded the fact that 4 squared is 16, either written this way, or that log base 4 of 16 is equal to 2, either or. Here it says log base 5 of 1 over 125 is equal to minus 3. So 5 is our base, negative 3 becomes our exponent, and the output of this is the argument here, 1 over 125. For the next few, they want us to find the exact values of these logarithmic expressions. I think it's fairly useful to create an equal sign where there is none, because we are going to be asking, what is this value? That's a kind of question. It equals what? By providing this equal sign, we can more easily see how this gets re-encoded in exponential form. And now this gives us a kind of exponential equation which we have seen how to solve before. So log base 4 of 16 is what? Well, this would mean 4 to the power of what is 16? And we know that 16 is 4 squared. We've seen in the exponential section that if we have like bases equal, their exponents must be equal because exponentials are a one-to-one function. They are injective. And so we can set the argument x and 2 equal to each other, which gives us our answer. 2 is the output. 2 is the value of log base 4 of 16. Likewise here, they say log base 12 of 1 over 144 is what? Well, that's 12 to the what is equal to 1 over 144. And you might see that this is 12 squared. It being on the bottom of the fraction means that's negative 2 instead. And so comparing the two exponents, we get that y is equal to negative 2. Here's another. Log base 4 of 1 over 1024 is what? Well, this means 4 to the what is equal to 1 over 1024. And there's a couple ways we could do this. I mean, perhaps you already know that 4 raised to the 5th power is 1024. But you might also just see that 1024 is from our doubling sequence, 2, 4, 8, 16, and so on. You do that 10 times, you're going to get 1024. And so we could also rewrite things this way, which I've done just to kind of showcase this exponential comparison. If I know that I'm dealing with not 4 to the z, but 2 to the 2 to the z, I have the product of 2z in the exponent. And 1024, well, that's 2 to the 10. 1 over 1024 is therefore 2 to the negative 10. Now I can just, since I've gotten the bases to be the same, equate the two arguments, 2z and negative 10. Dividing off my 2, we get that z is equal to minus 5, and that is the output of this logarithm. I should note before we go on, there is a way that you can use your calculator to check your work if the only question you have is, what is the evaluation of this particular logarithm? Going into the math section and scrolling all the way down to the bottom, we see a button called log base. Log base on some of the more modern calculators will allow you to input the base and the argument, which is going to let us confirm what we just found algebraically. Notice that there are already two buttons for logarithms if the base in question is either 10 for our common logarithm, or if the base is e. Here, for example, I've asked what power must I raise e to in order to get e, which is e to the 1, and that's of course just 1. It should be clear from the definition of the logarithm that no matter what exponent I put here, if this is the base of this logarithm, we should anticipate just getting that number back. Of course we do. These are inverses of each other after all, and in some sense, e to the power of is fully canceled by ln of. All right, let's move on to the next one. Here we need to remember that 1 over 17 can be rewritten as 17 to the minus 1. Then rewriting things in exponential form, it's easy to see that the output of this logarithmic expression must be minus 1. Likewise, we need to recognize that 1 over the 4th root of 11 is the same thing as 11 to the negative 1/4 power. Then because we're just taking the logarithm base 11, we're really just doing exponential comparison here to get that b, or the output of this logarithmic expression, must be equal to negative 1/4. This one asks, what is the log base 1/8 of 1 over 512? And what I'd like to do here is just sort of think through what would happen if I rewrote this in terms of base 8. So the first thing I've done is rewrite this output, which I'm going to call c, in this exponential form. Now, 1 over 512 we've seen is 8 to the negative 1/3, and 1/8 is 8 to the minus 1. Power to a power is a product of powers, so we get minus c as our exponent here, and then comparing the two, we can see that c is not negative 3, but getting rid of these two negatives, we have that c is equal to 3. And yes, that's true. We can always check our work the old-fashioned way by plugging in the value that we got and seeing that we get some reasonable output. Here, 1/8 to the 3rd power is 1 to the 3rd over 8 to the 3rd, but 1 to the 3rd is just 1, and 8 to the 3rd is 512. Here's a couple more for us. I have log base 1/4 of 64 is equal to delta. In other words, what power do I need to raise 1/4 to in order to get 64? This can, I think, more easily be seen if we rewrite things in terms of a base of 4 rather than a base of 1/4, which just puts this negative sign in our exponent. Now 64 is 4 to the 3rd, and so we know that negative delta must be equal to 3. In other words, delta is negative 3. Here I have another one with a fraction as a base, a fraction of 4/5, and it says, what power must I raise 4/5 to in order to get 16/25? And 16/25, if we look at the 16 to the 4, that's a square, the 25 to a 5, that's a square, and we have an output of this expression of 2. Remember, if you're ever very unsure about things, it's nice to confirm your intuition with technology, and a fractional base should be just fine to put down here in the base of the logarithm. With a 16 over 25 as our argument, we do indeed get a 2. Let's run through the next few. Log base 1296 of 6 is what? Okay, so let's just be patient and rewrite this in terms of exponential form. This is 1296 to the x is equal to 6. Well, a little bit of playing around and maybe some intuition would tell you that 1296 is a power of 6. 6 to the 4th, in fact, which means that this side of the equation is 6 to the 4x. Now, if that's 6 to the 1, then 4x must be equal to 1. And so x is equal to 1/4. And that would be the output of this logarithm here. Here's a fairly easy looking one. We have 10 as a base of 10 as the argument of the logarithm, which is asking us what power do I need to raise 10 to in order to get 10? Well, just 1. In fact, no matter what I put here, as long as it's some acceptable base, positive, real number not equal to 1, then the argument here, if it's equal to that base, we're just going to get a 1 as our output. This is sometimes written as one of our properties of logarithms. We'll talk about a full set of properties of logarithms in the next videos. Here's another good one though. We have log base 18 of 1 is what? Well, 18 to what power would give us a 1? Well, 18 to the 0th power would give us a 1. This points us in the direction of another property of logarithms, which is that for any admissible base, log of that base of 1 is equal to 0. Here we have another example of that. And here we have another kind of very simple problem. Notice the repetition of the base. They've actually listed the power of 9 that they want to take the log base 9 of. And this gives us an immediate and direct comparison. Same thing with our log base 6.6 of 6.6 to the 7, that's just 7. And in fact, both of the above special cases could be seen in terms of this particular cancellation property of logarithms, which again, we're going to go into more detail soon. Here we have some more running examples of these kinds of properties. Notice that this is a 1 with 7 zeros, which means this is 10 to the 7th. Log, well, remember if there's no base here, that's a base 10, and so we're asking what power do I need to raise 10 to in order to get this argument, which is 10 to the 7th? Well, 7, of course. The rest of these follow along very similarly. We just need to know what power of 10 we're talking about. 1 is the 0th power of 10, and so we're going to get an output of 0 here. Square root of 10, that's 10 to the 1/2, and so we're going to get a 1/2 for an output here. 1 over 100, that's 10 to the -2, and so we're going to get a -2 for an output here. And this, moving the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 times to give us a 10. This number is itself 10 to the -9. Well, that tells us that this output of the logarithm should be -9. This next cluster, recalling what ln means, is going to be very similar. We need to see what power of e our argument is, and once we do that, that's just our output of the logarithmic expression, right? This is ln of e to the 8/3, and so we get 8/3. This is ln of e to the 2, so we get 2. This is ln of e to the 1, so we get 1. This is ln of e to the -17th, and so that's our output. Here's another one where they dip back into the tens for some reason. That's 11/2 as an exponent. Don't be deceived by the fact that it's kind of dangling down here out of the superscript. That is an exponent of 11/2. And so 11/2 is our output. Alrighty, that's going to be it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.